Okay guys, so just to keep this one pretty brief and pretty simple, this is the law of reflection. This would be lab or station number 1. So if we're looking at this, the angle of incidence, or the angle at which the light is coming out of the ray box and hitting the mirror, is 50 degrees. Now, the law of reflection states that the angle of incidence should be equal to the angle of reflection. So we see that the angle of reflection is also at 50 degrees. Now if we shift this and we line it up so that we got the angle of incidence being equal to 30 degrees, and we put our mirror there, then the angle of reflection should also be at 30 degrees. Angle of incidence, 30. Angle of reflection, 30. All right, guys, let's go ahead and talk mirrors. So what we are looking at right now is a convex mirror. You can see its shape, how it kind of curves outward. Okay, we've got the curved shape going outward. Now, this one obviously allows me to see more of the room around me because of that shape. Okay, that's the convex mirror. The concave mirror, on the other hand, gives a significant zoomed in picture of what's going on. You can see this is huge. Now here's the interesting thing. As I back up with the mirror, watch what happens to my image. Oh my, what happened there? We have flipped upside down. Okay, now let's go ahead and talk about why we look upside down. If we were looking at this candle in the mirror, it works just like the pinhole camera here, guys, in the sense that the light from the top is going to hit the mirror, but look at the direction of the mirror. Look at the angle. Angle of incidence equals angle of reflection. So if it comes at, according to the mirror, at an angle, it's going to be reflected at the same angle. The same thing happens down here at the bottom. It's going to come in and be reflected. Now, what was on the top is now on the bottom, and what was on the bottom is now on the top. So this candle in a concave mirror would be upside down, just like I was in the concave mirror. All right, guys, let's go ahead and talk mirror images. So mirror images are the things that we would see when we were to look in the mirror. So if we pretend that that smiley face, see at the bottom there, is you looking into a mirror, and your nose is facing one way and the heart is facing the other. Hopefully you guys can see this. But if I take the mirror and you look at it, you can very clearly see what it would look like, right? Now the interesting thing about mirror images is that when you draw them, they are kind of the opposite, but they're kind of not. So like the circles are going to stay the same, the eyes are going to stay the same, but the nose will be pointed in the opposite direction. Smile, the same. The heart is actually going to go on the opposite side. If this was you looking into a mirror, let's say that that heart is on your right cheek, it's going to continue to be on the same side in the mirror. Same thing goes for the arrow right here. Hopefully you guys can see that. It's going to be the exact same arrow. It's just going to be pointed in at itself. That right there is a mirror image. Okay guys, this is the refraction station. So here, the very first one was to look at this rectangular prism. Take either your finger, I'm gonna use my thumb since it's a little bit easier for me, put it behind there, and then watch what happens when I rotate this. It appears that my thumb is being split, separated from the rest of it. And this is all because of what we call refraction. Because the light traveling through the prism is slowing down, because it's just like one of the example that I used the other day in class about pudding. If I were to swim through pudding, I'd look different than if I was swimming through water. Here, the light is traveling through the air versus traveling through the prism. It's going to look different when it travels through those two different things. Okay, here we go again with another example of refraction. Here's the laser going through the prism. Now, we can see it, light travels in a straight line, right? The laser goes into the prism and just continues on. However, if I change the amount of prism that the light has to go through by changing the angle, look at how the beam changes. So before it was going straight across, now it's very easy to change the direction. And if I switch sides from which it's approaching, watch this change. Very easy to change that beam just by changing the amount of plastic that light has to change through or go through. This is because the light is slowing down as it travels through the prism. This is a great example of refraction. Okay guys, I wanted to show you this stuff about lenses real quick. So this would be our concave lens. Now I want to show you just how different it makes it appear. Obviously the palm tree, when you're looking at it through the concave lens, is going to make it appear to be significantly smaller. Now if we look at the convex lens, you can see that it makes it larger. That is until we get to a certain point. I'm going to slowly move this convex lens away from the camera, and I want you to take note of what happens to this palm tree as I move further away. Notice the palm tree is now upside down. All right, now let's go ahead and talk about why this happens. So here's an example of our convex lens. And again, we're talking about why does the image actually flip upside down. And very similar to our pinhole camera, there has to be a spot in which the light rays cross. So the way that when the light goes through the lenses, what's on the top actually gets refracted and takes off in this direction. What's on the bottom gets refracted and takes off on this direction. And what's coming through straight just kind of continues to come through straight. This forms in the middle what we would call a focal point. But if you'll notice, what was on the bottom is now on the top, and what is on the top is now on the bottom. So if you were going to look at a letter T through this lens, the lens would now, or the T would now look like this on the other side. What was on the top is now on the bottom. What was on the bottom is now on the top.